And here we are with the topics right where we left off from the system called LSEEK, and the recording has started. Excellent. Any questions before we start? Okay. Well, in that case, let's continue with LSEEK. We have already witnessed the power of reading, writing, opening and closing. And now it is time to know how to move inside, of course, a file. I know that you have already met the C library equivalent, fseek, in the context of your previous studies, especially in C programming. But now let's take a closer look at what is happening behind the scenes in the world of low-level programming. Now, of course, a file descriptor that is obtained after opening a file, it will remember its position in a file. As you read and write, the cursor, imlech, the cursor, of course, will move depending on the number of bytes that have been read or written. Of course, you do not have to read or write in order to move the cursor. You can also move it arbitrarily. How? By using the system called lseek. It requires two header files, the ones that you see on screen, and I have shared my screen, right? Yes, I have. And it needs three arguments. Now, the first one is, of course, the file descriptor of the open file in which we are going to move the cursor. And then we have the offset and whence. Now, offset is simply a number, an integer, that can be both positive and negative, depending on the third parameter. And it expresses where the new position of the cursor should be. And whence, the third parameter of the system call, represents the reference by which we are going to count those bytes. So let's say, for instance, that somebody calls lseek with a certain file descriptor, and the offset is 100. So what does that mean? Well, if whence is equal to the constant seek set, that means we are going to have to move 100 bytes from the start of the file. Now, if you're using seek set as whence, offset can only be positive. If you're using seekcur as whence, that means we are going to move 100 bytes from the current position of the cursor, in which case the offset can be both positive and negative. And of course, if whence is seek end, in that case, we are going to move 100 files from the end of the file, also positive or negative. So that means we can go beyond the end of the file as well. And it will return a numerical value, an integer, representing the new position, always with respect to the beginning. Now, you can move inside any type of a file, device file, normal file, and so on, except for sockets. You cannot move the cursor inside the socket. That is a very special kind of a file. Here we have an example for lseek. So, for instance, if we use it with certain file descriptors with 0, seek set, so it goes directly to the beginning of the file with seek set. Seek end, it goes directly to the next byte right after the end of the file. So 0 is the next byte after the end of the file, not the last byte, right after the end of the file. -1, this is what we will give you the position of the last byte in a file. Seekcur, of course, is the constant that we have with respect to the current position, so cur for current. So -10 is 10 bytes prior to the current location, or 10,000 plus, or 10,000 would be 10,000 after the current position. But if you use, for instance, seek end, that means you are going to move 10,001 bytes past the last byte of the file. Now, let's look at an interesting example together. This is also an example from the Advanced Linux Programming book. And we use the lseek system call in order to create a huge file. How do you create a huge file? By simply telling the cursor to move past the end of this file, many bytes ahead. And so immediately as the cursor moves past the end of the file, well, the file becomes larger, the file becomes greater. How do you do that in practice? Let's see. We have the main function. It starts on the left. So we are going to create a file that is 1 megabyte. Okay, that is not really huge, but still, it contains 1,000,000 bytes. That's not negligible. So we have 1 megabyte right here, or yep. So we have the file name that we are receiving from the command line argument. That's nice. Okay. We are also receiving another command line argument, which tells us how many megabytes we are going to allocate in this file. Okay, that is also a numerical value. We convert it from ASCII to integer by using atoi as usual. Then we open the file. Okay, the file name came from the command line argument. We want to create the file. Okay, so we are using the ocreate flag. We are using O exclusive, so that means we are going to receive an error if the file already exists. And we are going to open it in write only. We do not intend to read anything, just for writing. And the permissions for the new file are going to be 666, which means reading and writing permissions for the owner, the group of the owner, and all the other users. So reading and writing permissions for everybody. Okay. And then after the file is open, what do? We go where we jump to 1 byte short of where we want the file to end. 1 byte short of where we want the file to end. Where do we want the file to end? At length. So we have a certain length. For instance, let's say the user entered 1000. So that means we want a file that is 1000 megabytes, so approximately 1 gigabyte large. So it will move that many bytes away from where seek set with respect to the beginning of the file. So we will have a file that is 1000 megabytes large. And at that position, so just because we move the cursor there, it doesn't mean that the file became that large. We also need to write at least something, just even if it is a single byte. So we write a single 0 byte at that position, a single 0 byte right at that position, and we're all done. We have a file that is empty in the beginning, but it has a 0 at the 1 billionth byte position. And then we simply close the file. Of course, this is not an excellent example. Why? Because we are taking no precautions against signals. We are not even checking the return values of the system calls. Now, any questions about this example? Okay, it is too early in the morning. Nobody has drank their coffees and teas yet.
Hocam sonra geriye dönüp tekrar yazabiliyor muyuz?
Who is this?
Ferdi hocam.
Ferdi. Yes, you can return to previous positions and write whatever you want. You have a file that is 1 gigabyte large. But it has nothing in the beginning. It is empty. It only has a 0 byte at the 1 billionth position. But another more interesting question is, does it occupy now 1 billion bytes on the disk? What is the size of the file? The size of the file, that's an interesting topic. That's why we have the next slide. Now, normally, well, it should definitely not be 1 megabyte because we are receiving an integer here. Be careful. We are receiving an additional integer as a third command line argument that will tell us how many megabytes to allocate. So is it equal to now, for instance, if we received 10, does it have a size of 10 megabytes? Or just because we have written 1 byte, it gets a size of 1 byte? That's a very good question. Now the name of the program is lseek huge, and now we are executing it. We are testing it to see what will happen. Now here, let's make this a bit larger. That's better. Now here, we are using the df command in order to see how much free space we have on our disk. And we can see that device HDA5, the fifth partition on our hard drive, has a size of 3 gigabytes. It's an old disk. And we have used 2.1 gigabytes, and we have 655 megabytes available. Now we execute the program that we just saw, lseek huge. We tell it to create a file named big file with a size of 1024 megabytes, so exactly 1 gigabyte. Okay, we executed it. So we created a file, and we put 1 0 byte to the 1 billionth position. So, and then we ls the file, and we can see it is right there. Big file, and it appears to have a size of 1 gigabyte. I mean, that's what ls says. However, if I execute df, which gives me information about disk usage, I see that the available space is still 655 megabytes. I mean, if we had truly created a file of size equal to 1 gigabyte, I mean, we wouldn't be able to even accomplish that. We don't even have 1 gigabyte left on our device. So, long story short, no appreciable disk space is consumed despite the enormous size of big file. Still, if we open big file, now this is interesting, if you try to open it, even though it does not occupy 1 gigabyte space, and you try to read from it, if you try to read from it, the OS, the kernel, will still return you, it will still show you as if the file is full of 1 gigabyte worth of zeros. So it's basically empty. So you can use, for instance, hexdump, the program that we wrote previously as an example for reading and writing. And if you try to read that file, you will see that it is full of zeros. So check that out. So this is a very nice technique from the world of POSIX. Now, these are known as sparse files, and they are very, very useful for representing a drive for a virtual machine. I'm guessing that you know about virtual machines. Do you know about virtual machines? Yes, no?
Yes, sir, we know.
Yes, you know about virtual machines. So in virtual machines, you have, for instance, you don't have an actual hard drive for the virtual operating system. You have files on the parent operating system that represent the hard drive of the what? Of the virtual operating system. But just because you have created a hard drive of, let's say, 10 gigabytes, so a file of 10 gigabytes, it doesn't mean that you have to fill it from day one with all that data and allocate that much space. So the technique is what? The technique is very simple. Allocate data as the file grows. Now, in the beginning, the virtual OS will not lead 10 gigabytes. It will maybe lead, well, I don't know, 500 megabytes or something. But as time progresses, it will store more and more data, and that file, which represents the hard drive of the virtual OS, will keep getting bigger. So while it keeps bigger, then the host operating system will actually allocate space for it. So basically, the kernel tries to trick us. It tells us that the file is there. When you try to read and write into it, you will be able to access it as if it is a true 1 gigabyte size file. But in reality, it only allocates space as it needs it. So it tries to be as efficient as possible. This is a really high-level technique. This is really good stuff. This doesn't exist in Windows. In Windows, if you try to do the same thing, it will give you done a 1 gigabyte file from day one. Ms. Gonja says, does it occupy space on disk? Well, it occupies only 1 byte at the moment, basically. Truly. Just the amount that you have written. Well, to be truly honest, not of course 1 byte, because there is a minimum block size, a minimum sector size on your hard drive, which is usually 512 bytes, depending on the disk. Sometimes it is 1 kilobyte. So it will occupy the minimum minimum amount of disk space that you can allocate on your hard drive, but not 1 gigabyte. The main idea is allocate space as you need it. But if the user tries to read or write from it to the user, and of course to ls, I mean, for everybody else who tries to access the file, the kernel always says, don't worry, it is a 1 gigabyte file. Don't worry about it. It is there, don't worry. Whereas in reality, it only allocates enough space just to keep you convinced. But for all intents and purposes, you can assume that you have a 1 gigabyte file even though you don't. Is this thing clear? Well, if you have any questions, feel free to type in, no problem. Now, let's take a look to the Swiss knife of input-output functions. Input-output control, IOCTL. Now, IOCTL is a system call that is reserved for everything other than open, close, read, write, and seek. Anything else that you want to do with a file other than opening, reading, writing, closing, and moving inside the file, for everything else, you have IOCTL. That's why I call it the Swiss Army system call. It does everything else that you can think of. Now, of course, since everything is a file in the POSIX world, and especially devices, and as you can guess, there are many things that you can do with a device besides opening, closing, reading, and writing. For instance, the simplest example. If you have a DVD-ROM, you can eject it and close it. That's an operation. You should be able to do that with a system call, right? So which system call is going to do that? You can have another device, some other custom device, I don't know, a sound card, maybe, and you want to make it do what? I don't know. What do you do with the sound card? It only plays music. A custom device. Custom device. Maybe you have some lights, a device with some lights, and you want to turn it on. Who knows? Anything custom, anything other than read, write, open, close, and LSEEK. That's why you have IOCTL, to do all that custom stuff. Now here, for instance, you can see it. It returns an integer value. It is only one header file to include. It manipulates the underlying device parameters of special files. It requires a detailed understanding of the device represented by the file descriptor. Now, this is not D, this is FD. You should correct that. There is a certain request, and you can see that there are 3 dots here. What is the meaning of these 3 dots? What is the meaning of these 3 dots? Ferdi Bey, mikrofonu açtığınız zaman konuşmuyorsunuz.
Pardon hocam.
Yeah. What was the meaning of these 3 dots?
It
Who
can
remembers?
take variable number of arguments.
Yes, it can take a variable number of arguments. Thank you. So, and that makes sense. That makes perfect sense. Why does it make sense? It makes sense because there might be devices that require 2, 3, 10, 5, who knows how many types of arguments. You don't know that. If you try to support all kinds of devices for all kinds of operations, well, in that case, you should be ready to accept all kinds of arguments in arbitrary number of parameters. That's why it has a variable number of parameters. So we have the request, the main request as a constant, usually, and of course, whatever parameter it requires. So let's look at a simple example. Here, for instance, we are trying to eject a CD-ROM. Sorry. We open the command line argument, which is the file representing the CD-ROM or DVD-ROM or Blu-ray driver or whatever you use these days. We open it in read-only. Well, since it is a CD-ROM, not a CD-ROM. Well, and then we call IOCTL in order to eject it. Very simply, the file descriptor representing the device plus the request. And then we close it. And it is as simple as that. It could, for instance, also accept additional parameters for that request, etc., etc. Now, we won't be we won't be spending too much time on IOCTL because it is it's beyond our scope. But just remember that whenever you need to do something at low level with a device other than opening, closing, reading, and writing, IOCTL, that's the address. That's where you go to. You give it the file descriptor of the device that you're interested in or special file or whatever, and plus the request along with its parameters. That's it. And leave the rest to it. If it makes a valid request that is understandable by the device, you should have no issues with it. Now let's get to something a bit more interesting, something that is within the scope of this course, and that is file, or rather FCNTL. Now, do not be fooled by the F at the beginning. This is not a library function. This is actually a system call. Now, this system call, which is short for file control, not input-output control, this is specifically file control, also receives a variable number of arguments, and it is for advanced operations. Advanced operations, not the special stuff like IOCTL does. This is for a bit more advanced operations such as locking files. I mean, in 90% of cases, that is what you use FCNTL for. Locking and unlocking files. What does it mean to lock a file? Locking a file means having exclusive access to a file, either for reading or writing. That means this file is mine for now, Who am I? I'm a process, and I'm telling all the other processes that this is my file now, I am using it, and nobody else can read or write, do anything with it. I have access to this file and me only right now. That's what it means to lock a file. Of course, after you unlock it, everything goes back to how it was, and anyone can do whatever they want with it as long as they have the permissions for it. Now, how does it work? Well, it can, of course, besides locking, it can manipulate the flags associated with the file descriptor. What flags? The flags that we used while opening it. So just because you use the flags O write only, for instance, for write only access, does it mean that that's it? You can never again change them? Do you have to close and open the file again to have new flags? No, not really. After even having the file open, you can still change those flags by using fcntl. Sorry, yes, fcntl. This is, there is a typo here. Sorry. It can also be used in order to duplicate file descriptors. So let's say that you have a file descriptor for an open file, but you want one more for it. I mean, at this point, you might ask, who in their right mind would like to duplicate a file descriptor? I mean, you have already opened the file. You already have a file descriptor for it. Why do you want a second one? Why do you want a clone for a file descriptor? That's a very good question. We will see such cases where we will need duplicates. Now, one way of duplicating file descriptors is by using fcntl. Now, how do you lock a file? It's very easy to lock a file. To place a lock on a file, you first create a zero out. So what does it mean to zero out? To fill with zeros. A struct flock variable. So you write a struct flock, you fill it with zeros. There is a L type in this struct. The L type field of the structure, you set it to F read lock if you want a read lock, or a WR lock if you want a write lock. Then you call the fcntl and you give the struct as a parameter to it, and along with, of course, the file that you want to place the lock on. And that's pretty much it. And as long as you do not call fcntl again in order to unlock it, well, it remains locked. Example. Here, for instance, in our main function, after having used, of course, necessary header files, we receive the name of the file as a command line argument. Here we have the struct flock, of course. So we open the file first. We are opening it in write-only mode, and then we will try to lock it. First, we fill with zeros the struct flock structure. The L-type field of the struct, we set it as WR lock, which means we want to place a write lock. Then we call fcntl with what arguments? The file descriptor of the file that we're going to apply the lock to. We are giving it the request. I mean, what are we going to do with that struct? We are telling it to set a lock. What kind of a lock? Well, all the details for the lock are present in the struct flock third argument. Okay, so we are going to use fcntl for locking. That's what the second parameter says. And the third parameter contains the details of what kind of a lock to place. Okay, as soon as fcntl returns, the file is locked, and it will remain locked. Until when? Until we unlock it. Now, what happens if we end the process and we do not unlock it? Well, if you terminate the process and you still hold the lock, well, in that case, since the process is terminated, then it is up to the operating system to clean up after you. And the operating system, of course, will remove automatically all the locks that you have placed. But of course, that is very bad practice. If you have placed a lock, you should always remove that lock before your program terminates. Now, in order to unlock it very easily, just a second. Sorry for that. Now, in order to release the lock, we are updating the contents of struct flock. Now, the L type previously was f write lock, and now it is f unlock. So we are going to use fcntl again with the same struct, but now the L type field has the request of unlocking. And once again, we are calling fcntl. with the same file descriptor. This is a locking-unlocking operation, and here are the details of that request. Once it is returned, once it has returned, the file is unlocked, and then we can close the file descriptor and all go home. Any questions about locking and unlocking? Mr. Ali says, when we try to write to the file before the get car, can we write to the file or do we get an error? No, you don't get an error. Why should you get an error? I mean, you have opened the file for writing. You have locked it with a write lock. Yes, you lock it, but by you, I mean this process that locked it has the key. So that means you can write to it, no problem. But no other process besides yourself, besides your process, besides this process, can write to it. So you have the write lock, and nobody else can write to it. If, however, this was a read lock, now the L type, this is a write lock, but it could also be a read lock. If it is a read lock, other processes can also read from it. They can also read from it. Now, that's what it says right here. Only one process can hold a write lock for a given file descriptor, but many can hold a read lock. In case of an already acquired lock, the call to fcntl will block the process. So if somebody else tries to also lock it while you hold the lock, they will be blocked. So let's say that we have two processes. Both of them want to lock it for writing. Now, you cannot have two processes that have a write lock at the same time. Only one process can have a write lock at a given time. So whoever gets the lock first, he is the one that is going to hold it until he unlocks, until that process unlocks it. So you can have multiple processes possessing a write lock for a given file, but only one process, you can have only one process possessing a write lock for a given file, but you can have multiple processes possessing read locks for a given file. Just like databases. I mean, it's the same idea. You can have multiple processes reading from a database. That's okay. I mean, it's okay to have multiple processes reading from a database. Nobody's hurting anyone. You can read before me, I can read after you. That's fine. We are all reading from the database. Nobody is changing it. But if you have multiple processes trying to modify, for instance, a database or a file, that's very dangerous. Very dangerous. Maybe I'm thinking of writing something, but who knows? Maybe somebody else came in there and wrote something at that position right before me or right after me. So in those cases, you cannot have multiple processes having the write lock at the same time. Only one process can have the write lock for a given file at a given moment. Anyone else who tries to acquire a write lock will be blocked. When? At fcntl. It will not return. So if somebody already has a lock on fcntl, using fcntl for a certain file, that process will be blocked and fcntl will not return. Class, I'm very sorry. There is someone at the door. I will be right back. Kapı çalınıyor. Hemen geliyorum. Very sorry for that. Now, Mr. Mustafa says, if you want to lock permanently, what should we do? By permanently, you mean even after the process terminates? If that is what you mean, it doesn't work like that. You cannot lock a file permanently. Mr. Mustafa, are you there?
Yes. Is there other system calls to realize that goal?
To lock a file permanently or to lock it temporarily?
Permanently.
Well, the only way for a process to own, well, the access to the files is determined, the permanent accesses, permissions for a file are determined by the permissions on the user level. So remember the read, write, executes? So in that case, when it says, for instance, that, for instance, if I create a file with the account Erhan, and I have read and write and execute or whatever permissions for it, all the processes that I create from my account, that I execute from my account, will also have access to that file in that way. So the processes also have an associated account name. So if my account, who has access to that file in terms of permissions, creates a process, that process will also have the permissions to that file to access it. But if the others group of users doesn't have the permissions to access the file, they will not be able, of course, to access it. Now, that is the permanent way of limiting access to a certain file. But locking it through a process permanently, no, it doesn't work that way. FCNTL is a lock, but once you acquire it, it is only valid during the lifetime of the process. When the process terminates, everything else returns to the operating system. Once again, it is the operating system that is in control. So whatever the process did, it terminates when the process terminates. And the lock returns to the kernel, and the file is open for access again to everyone who has permission for it. Mr. Anil says, when one process writing to a file, another process tries to write lock, then what happens? So you have one process that is writing to the file without a write lock, right? The first process doesn't have a write lock, Mr. Anil. Excellent. Now, two scenarios. Now this is not what you asked, I know. Two scenarios. One, if the first process that is writing to the file has a write lock, in that case, the second process that tries to obtain the write lock will block. As soon as it calls FCNTL, it will stop, it will freeze. Until when? Until it can acquire the lock. Then it will get the lock and return from FCNTL and continue the program. If, second scenario, what you asked, the first process doesn't have the lock, but is still, writing, it is a regular process. It opened the file, it is writing inside it, and somebody tries to acquire the write lock. Now, that is a very tricky situation. Now, this is what brings us to the topic that Mr. Yusuf, in fact, mentioned yesterday in the context of atomicity, tekillik. Now, imagine that nobody has a write lock, and you have two processes, both of them reading and writing from the same file. One of them is reading the first 10 bytes, and the other one is writing the first 10 bytes. Both of them in a loop, both of them, constantly reading, writing, reading, writing, reading, writing. Now, who is going to read what, write what, in what order? I mean, is it possible? Is it possible for one process to read some of the bytes that the second process tries to write before the second process completes writing? Is there a certain guarantee that one process will complete its writing before another process attempts to read or write? Now, that's a very tricky point, and that is what Mr. Yusuf was asking about yesterday in terms of atomicity. Now, in the world of Linux, not POSIX, in the world of Linux, there is a certain small guarantee, but that guarantee is very small. It is just a few bytes, and it is only valid, by few bytes I mean a few hundred bytes, and that is only true for a certain type of file, which we haven't seen yet, and it is called a pipe. If your file is of the type pipe, then there is a guarantee that when you try to read or write, no other input-output operation can intervene before you finish it. So if you try to read 512 bytes, you will be able to read those 512 bytes without anyone else interfering and writing something at that position. But that is very specific to the world of Linux. In the world of POSIX, so in generally speaking, in the world of portable operating systems, there is no such guarantee. So while you are reading or writing to a file, somebody else also might try to attempt the same thing. So there is a danger, a very significant danger. So if you want to be certain that nobody else is messing with your file while you are doing something, you must lock it. You must lock it. So long story short, is there a guarantee that somebody else will not interfere with your reading or writing if you don't have a lock? No, there is no guarantee. In the world of Linux, there is a very small guarantee for a certain type of a file, but it's really negligible. In the general world of POSIX, no, there isn't really a guarantee. Anything that can go wrong will probably go wrong unless you take precautions for it. And how do you take precautions? By locking the file. By locking the file. Now, if of course this is just a file that you just created or a file that is specific to your application, well, very probably nobody else is interfering with it. So you can safely assume that you are the only person dealing with this file. I mean, that's why applications have their application-specific files, so that nobody else will be, well, possibly touching them or modifying them. But is there an ultimate guarantee, a 100% guarantee that nobody else is messing with that file while you are working with it? No, there isn't. So when one process is writing to a file, if another process tries to obtain a write lock, what will happen? Well, it will obtain the write lock. It will obtain the write lock after the other process has finished writing with it. Very possibly, but without a guarantee. Without a guarantee. So if you want a guarantee, gerçekten emin olmak istiyorsan, arkadaş ben bunu buraya yazmak istiyorum ve yazıldığından da başka birisi araya girmeden de bunun buraya yazıldığından da emin olmak istiyorum diyorsan alacaksın kilidini güzel kardeşim. In 99.99% of cases, nothing wrong will happen. But just when you try to show it to your boss, well, you never know. Any questions?
Hocam herhangi bir sinyal gelse de yine çalışmaya devam eder mi?
Kim? Kim çalışmaya devam eder?
Bloklama işlemi.
Bloklama işlemi. What happens when you receive a signal while you hold the lock? Well, depends on the signal. If, for instance, you receive a SEGV signal, which is the signal for a segmentation fault, everything terminates. I mean, many signals override locks and everything. So let's say that you have a process that has locked a file, and you receive a segmentation fault signal, or a kill signal, or a termination signal. Something that you cannot postpone, something that you cannot stop. You are receiving an order from the operating system to terminate. Well, then you terminate. All the locks return to the system, everything is unlocked, and that's it. But if it is, for instance, a signal such as USR1, USR2, which are signals that can be ignored, can be handled, well, in that case, you continue to hold the lock. We will talk about signals when we talk about signals. Any other questions? Main things to remember.
Hocam bir de bu bloklama işlemine belli bir süre verebilir miyiz mesela? Şu kadar
Hayır.
kilitli kalsın.
Ha, şu kadar kilitli kalsın diye. I'm not sure about that. You have to check the man page of FCNTL. But in general, when you acquire the lock, there is no time limit to it. So as long as you do not unlock it, it remains locked, and your process continues to live. Main things to remember with FCNTL and locking and unlocking. Only one process can hold a write lock at a given time for a given file. Multiple processes can hold read locks at a given time for a given file. Once you lock a file for writing, anyone else who tries to lock it for writing will be blocked, will not be able to lock it. If they try to access it for writing, they will not be able to access it for writing. They will receive an error saying that the file is locked. So when you have a write lock access to a file, you are the only process that can write to it. The only process that can modify it. And as long as you do not unlock it, nobody else can unlock. Nobody else can write to it. That's the whole idea, basically, the summary of it. Now, a few words about redirection. Now, I'm sure that you have tested these waters before. I'm sure that you have used redirection before. This is the greater than sign that you use on the terminal. So what is the idea? It's very simple, very simple. Under normal circumstances, a process reads from standard input and outputs to the standard output. That's what happens by default. And if there is an error, the error message is sent to standard error. But of course, this doesn't mean that we cannot redirect them. This doesn't mean that you cannot redirect standard output to somewhere else or standard error to somewhere else. Maybe you want standard error to not go to the monitor, but to go to the log file. Now, you can, of course, do this in your actual program. Inside your actual program, you can code it that way. You can standard error. It is file descriptor number 2. You can close 2 and open it as something different. That's possible. But here we are talking about doing it outside of the program, at the command line. So, for instance, my script can be a program that you have written, or maybe a program that somebody else has written. So you can manipulate what will be the standard input, output, and error files or channels of this program outside of this code from the command line. How? Very simply. For instance, in the first example, we are telling the operating system to execute the program MyScript, but greater than results.log, we are telling it to associate file descriptor number 1 for MyScript with results.log. So whatever printfs happen in MyScript, whatever MyScript program tries to print on standard output will go to results.log. And not only that, we are also telling it to reorient, to redirect file descriptor number 2 to file descriptor number 1. Now, what is file descriptor number 2? It's standard error. What is file descriptor number 1? Standard output. So we are telling it to redirect standard error to whatever or wherever standard out points to. And where does standard out point to? It points to results.log. So basically, in this simple command, we are telling it to send all messages of standard output to results.log and also all the standard error messages to results.log. Any questions about this command? And then another example. Here, once again, we are telling it to redirect standard error to standard output. So 2 is redirected to 1. But not only that, we are also telling it through a pipe, the pipe operator, to use all the output produced by MyScript, so all the errors and, of course, standard out messages that are produced from MyScript as input for the program less. So we are redirecting the output and standard error of MyScript to the standard input of less. So basically, we can redirect anything from the command line with no need even to get into the programmatic aspect inside the actual executed process. Any question about redirection? Of course, you have used this stuff before, right? This is not the first time that you see redirection. I hope. Okay, everybody's silent. I'll take it as a yes. You know about redirection, but how does it work behind the scenes? Now, let's look at the system programming part of it. Just because you have used those commands, what happens behind the scenes? What happens to the file descriptors? Because we know that 0, 1, and 2, they open automatically. But how do you redirect them? Now, what is used behind the scenes is a system called dup2. Now, if there is a dup2, that means very probably there is also a dup1. And yes, there is. There is a dup, there is a dup2. Here we have dup2. Now, it is very simply used in order to duplicate, in order to make a clone of a file descriptor. So it makes a duplicate of the file descriptor. It receives two arguments. So you give it, for instance, the old file descriptor and the new file descriptor. And the new file descriptor becomes a copy of the old one. If, for instance, you give it as old file descriptor 2, which represents standard error, and you give it a new file descriptor of 3, then 3 will also be a file descriptor pointing to the same file. So you will have two file descriptors basically pointing to the same thing. Now, it makes a duplicate of the file descriptor given an old FD using the descriptor number supplied in new FD. If the file descriptor specified in new FD is already open, well, in that case, it closes it first. For instance, if we call dup2 with 1 and 2, so standard output and standard error, it will do what? It will create a copy of standard standard output, also with file descriptor number 2, but since 2 is open as standard error, that means it will also close it first. So 2 will also be pointing as a file descriptor. 2 will also be pointing to wherever is standard output pointing. So whatever somebody writes to 2 with the intent of expressing an error, they will send it to the same destination as standard output. So this is the same thing as writing 2 greater than &1. So first it closes 2 and then reopens it as a copy of 1. Or you can also do the same thing with FCNTL. FCNTL also can be used in order to duplicate file descriptors. So you just give it as a first argument the file descriptor, the original, the old FD. The second parameter which tells FCNTL what to do. Previously we had used setlock. Here we are telling it to duplicate a file descriptor. That is our command. And then the parameter which is startFD. And it will use as new FD the lowest unused file descriptor greater than or equal to startFD. It is as simple as that. Most of the time we use dup2. Why? Because it requires 2 parameters and not 3. It is easier to use. It is shorter. So if you ever need to duplicate a file descriptor, dup2 is the way to go. Any questions about redirection?
Sure, I think I just missed what dup1 does.
We didn't talk about dup1. We didn't talk about
didn't?
dup1, and we will not talk about dup1, not yet. Not yet.
Okay.
Dup1 does the same thing as dup2 with a very minor difference, but it's an important minor difference. We'll talk about it when the time comes. Now, this brings us to the topic of file implementation, and we still have approximately 10 minutes. Approximately, that is enough time to handle it. Now, there are a few things that I want to say about file implementation in the world of POSIX. And you will see much more in detail in the course of operating systems, or maybe you've already seen it, I don't know. But there are certain things that we need to mention in the context of this course as well. Now, a very important principle in the world of POSIX when it comes to file implementation, when it comes to implementing a file system, is separating data and metadata. What does that mean? Now, files contain data. Files contain data. They contain binary data, they contain ASCII data, they contain data. No matter what they are, files are there to contain data. Now, files have a lot of metadata. They have the owner of the file. They have the date of creation, date of modification, the file size, the date of last access, all the permissions, the owner of the file, the group that owns the file, etc., etc., etc. All that metadata as well. Now, one way of organizing a file system is to have one data structure representing a file, and you keep in that data structure both the data and the metadata together as a single unit. In POSIX, and also in Linux, data and metadata are kept separately. This provides many advantages. Now, the metadata is kept in something called an inode, which is short for index node, and it is a fixed length structure. So it has the same size for all the files, regardless of the size of the file. It has always the same size. This inode contains all the meta information, all the file size, file location, where the file is on the hard drive, the owner, time of creation, time of last access, etc., etc., etc. All of it is kept in this fixed size structure called an inode. Now, the inode, in addition to descriptive information about the file, all the metadata, the inode also will contain pointers. Pointers to what? The first few data blocks of the file. Data blocks. Now, the block is the minimum unit of storage in your file system. On my system, for instance, it's 1 kilobyte. On my system, the size of a block on my file system is 1 kilobyte. So the inode of a file contains pointers to such blocks. Now, if the file is large, remember, the inode has a fixed size. Now, if the file is too large, so it has many thousands, hundreds, maybe millions of 1 kilobyte blocks, that would be really huge. The indirect pointer, if the file is large, there is an indirect pointer, which is a pointer to a block of pointers that point to additional data blocks. But if the file is still larger, then the double indirect pointer is a pointer to a block of indirect pointers that point to data blocks. And of course, if it is really huge, there is also a triple indirect pointer that contains a pointer to a block of double indirect pointers. So it looks something like this. So on the left, we have the inode, which contains all the meta information of the file. Now remember, there is no data, no file data in the inode. There is no file data in the inode. It only contains the metadata, and it only contains a few addresses, pointers, to the data blocks. Now here you can see the direct data blocks. If the file is really small, so just a few kilobytes, this is all it needs. Just a few data blocks, and there you go. That's where the file data is. Those are the addresses on the hard drive where you can find the data of that file. And of course, there is no need for these data blocks to be contiguous. Yan yana olmak zorunda değiller hard diskte. They don't have to be these data blocks right next to each other on the hard drive. One of these data blocks can be at the beginning of the hard drive, another block can be at the end of the hard drive, and so on. In that case, we say that the file is fragmented, which is something really bad in terms of efficiency. Because just in order to read a file, that means the hard drive has to visit 3 different places, far from each other, and it takes a lot of time. So ideally, we should have contiguous, birbirine ardışık, yapışık bloklar on the hard drive. But if again, you do not have, but if again your data is too much, so the file is too long, well, in that case, you can use the single indirect pointers as well that point to a block, to an entire block, a 1 kilobyte block, which points also, which contains addresses of data blocks. And if that is not enough, you have the double indirect field, which also points to another block, which points to blocks that only contain addresses of data blocks. Or you can also have the triple indirect, 3 levels of indirection. And your exercise, not homework, and your exercise is, for instance, to calculate for such an inode with a 64-bit addressing operating system, what is the maximum supported file size? I mean, what is the maximum supported file size? How many data blocks can we point to if we use the entire capacity of an inode, knowing that we have a 1 kilobyte block size and that the system has x64-bit addressing space? That would be interesting. That is an exercise for you. Any questions about this file implementation in the world of POSIX? What about directories? Well, inodes, yes, they contain the information for data files, but directories, they don't have data. What are directories in the world of POSIX? Now directories, now this is where it becomes really interesting, and we start to see the advantages of using inodes, the advantages of separating data from metadata. A directory in the world of POSIX and Unix is simply an associative array. An array where we associate the inodes of the files that it contains, the inode numbers, and the names of the files. If you look here, you will see that there is no file name. Where is the file name? The file name is in the directory. So a directory is basically
Hoca düştü mü?
yok, hoca burada. Sorry, I think there was a glitch. Can you hear me now?
Yes, we do.
Yes.
Yes, excellent.
Your,
As I was saying,
your
as I was
image is
saying,
broken.
my image. Okay, I can turn off my image, no problem. You don't have to see me, as long as you see the screen. Now the directory. What you need to remember is that the inode itself does not contain the file name of the file. The name of the file, of any file, is stored in the directory as an associative array. So the directory, a folder, if you will, it only contains pairs, çiftler, pairs of inode numbers, inode'ların numaraları, indeks numaraları, and the name of the associated file. So let's say that you try to change the name of a file. Or let's say that you try to access a certain file name. You try to open the file named myfavoritefile.txt. In that directory, the system will see what is the inode number right next to it. It will go with very low complexity, constant complexity even, to directly that inode, 1,167,626, and access the position of its data. So when you try to access it by a file name, what is actually happening is in that directory, the system, the operating system, finds out what is the index node number of that file corresponding to that name, for instance, to bar file, and uses that number to reach the inode. And in that inode, it figures out where is the data on the hard drive. Now, if you try to change the name of the file, well, in that case, that's very easy. You simply go to the directory and change this string, and that's it. You don't even have to access the hard drive in order to change the name of a file. And even better, if you try to move a file, a very large file, you do not even have to touch the hard drive. Let me repeat that. When you try to move a file from one position to another on your file system, you do not actually move the file on the hard drive. You simply modify, you simply take the name of this file from this directory and put the name into another directory, and that's it. But you're not actually moving the file on the hard drive. So changing the file name only requires changing the current directory entry. A file can be moved from one directory to another by simply moving the directory entry, as long as we're on the same partition. You do not have to have more than one physical copy of a given file, but the file, of course, can have several names in different directories. You can, of course, have directory entries of variable length, but always remember that the inode structure is of fixed length. So these are the two main advantages that we have for separating metadata from data in the context of file organization of the POSIX world. And now the time is 9:30. We have finished half our slides for this week. That's good. And we will continue next week, if everything goes all right, on Wednesday morning at 8:30. So good luck with your next course. And if you have any additional questions, feel free to send emails. See you next week. Katılım için teşekkür ederim arkadaşlar. Haftaya çarşamba günü görüşmek üzere.
Have a nice day, sir.
Thank you. You too.
Have a nice day, sir.
Thank you, class. Goodbye. Arkadaşlar siz çıkmayı düşünüyor musunuz? Da takılacak mısınız?